Okay, I want to go through an example of using extent to solve a reaction problem. And I've gone through and I've already set up and drawn this problem. It's an example basically taken from the book, but I want to go through the thought process of solving this problem and using again extent to solve it. So let's just start out with this. We got this reaction right up here at the top. So this is a complex reaction with 3 reactants, 2 products, C3H6 plus NH3 plus 3/2 O2 goes to C3H3N plus 3H2O. So again, reactants, products, and we have this reactor where we have a feed coming in, and it reacts according to this equation, and then we have an outlet. The feed is 100 moles, and I just wrote 100 moles, but this could be in terms of time, moles per hour or whatnot. We're just assuming we have a fixed amount of 100 moles and it reacts for some set amount of time. We have different mole fractions of the different species. In this case, we have 3 reactants right here, C3H6, NH3, and O2, and different mole fractions, and then we have some N2. And the reason why we have N2 is because O2 and N2, this is basically the composition of air. So in this case, we have C3H6 and NH3 reacting with air, and since air is mostly nitrogen, we do have some nitrogen that's coming in the inlet stream, but it does not react. It just is a neutral, inert species that's coming through our reactor. And we don't know anything about any of the flow rates or the actual amounts of different species coming out. And here's the various different species. We have our 3 reactants, we have products, and then we have that N2 that since it was coming in. So we don't know any of these, and this is what we want to try to find. But we're told that the fractional conversion of the limiting reactant is 30%. So if we can determine what the limiting reactant is, we can use this knowledge about the fractional conversion to find out how much of that limiting reactant reacts or is converted, and then from there we can go through and find how much of the different species react and find out how much leaves the reactor. So first thing we need to do is go ahead and find out what is the limiting reactor, or the limiting reactant. So let me just move this off to the side here. So what we need to do is go ahead and look at the amounts of the various species and compare them to the stoichiometric ratio. So again, we'll first write out here number of moles of NH3 over the number of moles of C3H6. Those are 2 reactants coming in, and that would be 100 times 0.12 over 100 times 0.1. So this right here is just the number of moles coming in, 100 times the mole fraction. And so the units of these are mole and mole, but they all cancel out, so this is equal to 1.2. Well, this 1.2 is greater than the stoichiometric ratio, which is 1 mole of NH3 to 1 mole C3H6, and I just got this right here, the stoichiometric ratio, from the coefficients here on the in front of the reaction. So this tells us right here that since the actual ratio right here, 1.2, is greater than the stoichiometric ratio, that tells us that NH3 and the number of moles of NH3 is in excess compared to the number of moles of C3H6. So there's more NH3 than C3H6 compared to the stoichiometric amount. So we may be tempted to say, okay, NH3 is in excess, C3H6, that's our limiting reactant. But we still need to look at the O2 because that's one of the other reactants. So next we'll look at the ratio of O2 to C3H6 and O2 to NC3H6 is equal to 100 times 0.16, 100 times 0.1, and again those are just the amount of moles multiplied by the mass or the mole fractions to get the total number of moles, and that is equal to 1.64, which is greater than the stoichiometric ratio, which is 1.5. And I got the 1.5 simply by taking 3/2 divided by 1. So this tells us NO2 in excess compared to NC3H6. So we've looked at all the different species that are present, and we know that the O2 is in excess, NH3 is in excess. So again, O2 and NH3 are in excess compared to C3H6. So C3H6 is the one that's in the slowest stoichiometric proportion. So C3H6 is our limiting reactant. So C3H6 is the one that we'll use when we're examining the fractional conversion of the limiting reactant, because C3H6 is that limiting reactant. So I could, if I wanted to, determine what the fractional excess is for C3H6. Determine the fractional excess for NH3 and O2. There's no fractional excess for C3H6, but I could determine those if I wanted to by using the appropriate equations. But I'm not going to, since we're focused on this point calculating what these outlet streams are, but we could do that. In any case, let's look at the fractional conversion and use that to help us determine what's going on here with this system. So in this case, fractional conversion is equal to the number of moles reacted over moles fed, and that's 0.3. So at this point we could go ahead and solve for the number of moles of C3H6 that were reacted, but I just want to show you one other alternative way to do that, and that's to use the fraction unreacted. So the fraction unreacted is just simply 1 minus the fractional conversion. And sometimes you may see this written as F, just the fractional conversion of F. I just write it out as CONV, which just means fractional conversion. But the fraction that's unreacted is equal to 1 minus the fraction converted. And the fraction unreacted is the fraction that's remaining after it goes through the reaction. And in that case, it's just 0.7, which tells us that 0.7 or 70% of the inlet is left over after it goes through the reactor. So if I just write up here NC3H6 out is equal to 0.7 times NC3H6 in. And so that's just the amount leaving is the amount that's left over, or the fraction unreacted multiplied by the amount going in. And so this is just a handy way to quickly find out what's exiting the reactor if we know what the fractional conversion is, or vice versa. Conversely, we know the fraction unreacted. So in any case, the amount going in is equal to 100 moles times 0.1, so naturally we have 10 moles coming in. So if I go ahead and do that, I get 7 moles leaving C3H6. And that's the amount coming out of our system, C3H6, 7 moles coming out. Okay, now that we know this amount, the amount coming out, we can use our extent of reaction to go ahead and solve for all the different other species that are coming out. So the equation we want to use to find out our extent is N out is equal to N in plus the stoichiometric coefficient there, multiplied by the extent. So we have all the information here about C3H6. The amount leaving is 7 moles. That's what we just calculated. And that's equal to the amount coming in, which is 10 moles. And then we have to take into account the stoichiometric coefficient. In this case it's 1, but since it's a reactant, it's -1 minus the extent. So here, straightforward, go ahead and solve this for extent. We get extent is equal to 3 moles. And from here, it's very straightforward what we need to do to go ahead and solve for all the different species coming out of our system. So I've just rewritten the extent up here in the top right, and we just need to use our extent equations. So in this case, NH3 out is equal to NH3 in. In this case, it's minus the extent because the stoichiometric coefficient is 1, but it's a reactant, so it's -1. And I can go ahead and figure it out for what NH3 out is. In is 12 moles, which is 100 times 0.12. So, and we know what the extent is. So 12 minus 3 tells us that the amount of moles of NH3 out is equal to 9 moles. And I can write another equation for O2, and that's just equal to NO2 out minus 3/2 the extent, and I can go ahead and solve this. I know everything in here except this part. I know this, it's given, and I know this right there, and I can go ahead and write O2 out. And if I do the math right, I get 11.9 moles, around 11.9 moles, and then finally we have NC3H3N is equal to the amount coming in, but it's 0, so the amount coming in is 0, we don't have any in the feed, and then that's going to be equal to plus the extent, so that's good. It's equal to 3 moles, and I can do this also for the water. In the case for water, we'll have a 0 here for the inlet, and then we'll have 3 times the extent, so the amount of water coming in out of the system is equal to 9 moles. Put little boxes here. The only thing left we have to find here, if I'm looking at this correctly, is the amount of N2. Well, N2 is not involved in any of the reactions, so whatever inlet N2 goes into the system, that's what comes out of the system. So N2 is equal to 62 mole. Little box there. And that's pretty much the problem here. We've gone through and we've first initially determined what was the limiting reactant, in this case C3H6, and then used information that was given in the problem about the fractional conversion of the limiting reactant to find out how much C3H6 we have leaving our system. And remember, just remind you, we use the fraction unreacted. It's just an alternative way besides the fraction reacted. We use that to find the extent, and then once we know the extent, we just use the same equation over and over. The amount going out is equal to the amount going in plus the stoichiometric coefficient multiplied by the extent, and we just use this equation over and over until we get to, in order to get the amount of different species, chemical species, leaving our reactor here. And that's it. That's the problem here. Again, illustrating how we use extent to solve a problem. And again, Once we know this extent, we know a lot of information, and we can apply it to all of the different species in this reaction to find out how much is reacted and how much comes out of our reactor. And that's the power of extent.